Okay, so here's the problem. We want to find, if possible, the absolute maximum and minimum value of the function x plus 1 over x on the interval excluding 0 all the way up to positive infinity. Now why do I say if possible? Well, let's see. The extreme value theorem guarantees the existence of an absolute maximum and minimum value for a function on an interval if two conditions are met. If the function is continuous on the interval, well, let's verify. X plus 1 over x is continuous everywhere on the real line except for when x is equal to 0. As we exclude, that's what the round bracket means, we start at 0 but we exclude 0, and so 0 is not an element of our interval, therefore our function is continuous on the interval. So the first condition of the extreme value theorem is met. But there is a second condition, and that condition is that the interval must be closed and bounded. Well, this interval is neither. The left endpoint is excluded, so this interval is open, not closed, and it's also unbounded as we go all the way up to positive infinity. So because the second condition of the extreme value theorem is not met, the function may or may not attain a maximum and or minimum value on this interval. And this is why I said if possible. Well, let's inquire. Because we know if, and now the word if is very important, if there is a maximum and or a minimum value for this function on this interval, it must happen at an endpoint of the interval or at a critical point inside the interval. So let's look around those points. There is no right endpoint, that's pretty clear because we're going all the way up to positive infinity. We could think perhaps of 0 as a left endpoint even though 0 is excluded. So let's look at our critical points first. To find the derivative of f, it is easier to rewrite 1 over x as x to the negative 1 and use this with the power rule instead of the quotient rule. And so f prime of x, our derivative, will be quite simply 1 power rule minus x to the negative 2, which you can of course rewrite as 1 minus 1 over x squared, or as a single fraction. This is x squared over x squared, therefore x squared minus 1 over x squared. That is our derivative. Well, let's find our critical points. First critical points where the derivative is equal to 0. Well, as our derivative is a single fraction now, a fraction can only be 0 if the numerator is 0. So x squared minus 1 must be 0. Add 1 on both sides, so if x squared is 1, and here there are two solutions. If x squared is 1, x could be negative or positive 1. But again, remember that we are only interested in critical points inside of the interval. 1 is inside our interval, not negative 1. Negative 1 is outside the interval, and so we reject it. So we only have one critical point where the derivative is 0 that lies inside of our interval. Well, what about critical points of the second form, where the derivative is undefined? Well, we have once again a rational function. The only way for this function to be undefined is a division by 0. Therefore, if x squared is equal to 0, but obviously x squared can only be 0 if x itself is 0. But we will end up rejecting x equals 0 as our interval is open at 0, and so 0 is rejected. So there really is only one critical point inside of our interval. But the question now is, well, where do we go from here? Right? Normally, if the interval was closed and bounded and the function was continuous on the interval, we would construct our table of values, and we'd figure out what is the maximum and minimum value from our table of values. We have no endpoints here, so we can't just do a table of values. So here what we'll do is we'll fall back on producing a rough sketch of the function, and we'll study the function around the points of interest, namely our only critical point where the derivative is 0, and we'll study the function around 0 and around infinity when x is very large. First, x equals 1 is a critical point where the derivative is 0. Well, can we tell more? Is the function there concave up, concave down? What happens? Well, we'll figure this out if we fall back on our second derivative. Well, the derivative of the first derivative will give us the second derivative. If you differentiate 1, you get 0, minus power rule, you'll bring the exponent down, you'll get negative 2 is plus 2, times x to the negative 2, negative 1, negative 3, which is quite simply 2 over x cubed. And now here, if you plug in into the second derivative the value of your critical point, so the second derivative at 1, you get 2 over 1 cubed, which is simply 2. And we don't care that it's 2, but that it is positive. So the curve is concave up at 2. And remember, if the second derivative is positive, the curve is concave up. If the second derivative is negative, the curve is concave down. So we know what the graph of our function will look like around x equals 1. At this point, the curve is flat because the derivative is 0, and the curve is concave up. Therefore, the graph must give us a local minimum. Concave up and flat around x equals 1. We can actually say more, because we could think, well, are there points of inflection? Points where concavity changes? Well, look at our interval. We're considering an interval where the values are only positive. So, if x is positive, which is our case, look at your second derivative. If x is positive, so is x cubed. 2 over a positive value is positive. Therefore, for every value inside our interval, the second derivative is positive. And so not only is the curve concave up at 1, it's concave up everywhere for positive real values. On, of course, our interval from 0 to infinity. Alright, so let's put what we have so far in a slightly larger picture. We are considering only non-negative values of x. We know that at x equals 1, we have a local minimum at least around 1. The curve there as a derivative of 0, so it's flat. And we can ask, well, what is f of 1? What is the y value there? Well, f of x, if you recall just by looking back up, is x plus 1 over x. And so f of 1 will be 1 plus 1 over 1, which is 1 plus 1, which is 2. So the y value at x equals 1 is 2. So we know what happens locally around x equals 1. But what happens everywhere else in our interval? Well, the answer is not much, right? The only critical point we found for positive values of x was x equals 1. So because there are no other critical points to the right of 1, and the curve is increasing, it will remain increasing forever. And the same thing to the left. There are no critical points between 0 and 1, and so the curve is decreasing there, so it will always be decreasing between 0 and 1. And the curve is always concave up, so the curve will always look like this. The only question left is, well, what will happen to the function when x goes to positive infinity? I mean, there could be a horizontal asymptote, or some way that we approach a fixed y value. Maybe that will give us a maximum. Who knows? Same thing for the question of what happens to our function as x approaches 0 from the right. So let's look at these two questions. So first, let's approach 0 from the right. The function is x plus 1 over x. Well, as x goes to 0, x goes to 0. But as x goes to 0, 1 over x goes to, because x is positive, positive infinity. And so the limit is positive infinity. So as x approaches 0 from the right, the function will get bigger and bigger and bigger. So it will not give us an absolute maximum, it will keep increasing. So x equals 0 is a vertical asymptote. What happens when x goes to positive infinity? The function again is x plus 1 over x. And that's kind of the opposite behavior. The 1 over x term will give us a 1 over infinity, which shrinks to 0. But x goes to infinity, so the limit is infinite. So as x gets bigger and bigger and bigger, so does the function. And now we clearly have the full picture. We produced a rough sketch of our graph for positive values of x, and we can write our conclusion. The function does have an absolute minimum value, which occurs at 1, and the minimum value attained is 2. As we've just said, the minimum value attained is y equals 2. And it occurs at the absolute minimum, x equals 1. Well, alright, that's the absolute minimum. What about the absolute maximum? And the answer is pretty simple. There is no absolute maximum. Y can be as big as you want if you take x bigger and bigger, or also closer and closer to 0. There is no bound for how big y can be, so the function has no absolute maximum. And that's our conclusion. And this is okay, because the function was continuous on the interval, but the interval was not closed and bounded. There was a possibility of having a max and a min, a max and not a min, or no max and a min, or none whatsoever. Here, as it turns out, we had an absolute minimum, but no absolute maximum. And so, this should be your conclusion now. If the function is continuous, and the interval is closed and bounded, by the extreme value theorem, you are guaranteed a maximum and a minimum value inside the interval. So you find your critical points, your endpoints, look at your table of values, and you're done this way. If one condition or more of the extreme value theorem are not satisfied, then fall back simply on sketching a rough picture for the graph of the function, and this will tell you quite clearly if there is a max or a min or not. And that's it.